Hello, my name's Thanom and I'm from UNSW. Today I'm working through one of the MATH1011 Calculus class tests. So, question 1 of this particular test asked us to find f dash of x given f of x was the natural logarithm of sine of x. So this is a composite function here. It's the logarithm of sine of x. So we'll need to use a chain rule. So if f of x equals log of stuff, then f dash of x equals 1 over stuff. That's the rule for log. Log of x differentiates to 1 over x, so log of sine of x differentiates to 1 over sine of x. The chain rule, however, says that in addition to this, we need to make sure we multiply by that inside differentiated. So we need to multiply by the derivative of sine x because we have a function of a function here. So we have 1 over sine x multiplied by the derivative of sine x is cos x. So we end up with cos x divided by sine x or cot x as the derivative of log of sine of x. Question 2 is asking us to evaluate this one-sided limit. So we can see it's the limit as x approaches 1 with a little superscript of a minus. So this means x approaches 1 but from the left. So we're not approaching minus 1, we're approaching 1 still but from the left. Now the reason we need to do that is because we can see this expression here has an absolute value. And so it's not necessarily true that the limit from the left and the limit from the right will be the same thing. So one of the first things we might try is to substitute x equals 1 in, but we can see if we do that we'll get 0 divided by 0, and we can't deal with 0 divided by 0. We'll need to simplify that expression. So if we want to simplify this expression, first of all we'll need to sort out this absolute value here. So let's just examine the absolute value of x squared minus 1 first. So just x squared minus 1 is a parabola. It's a parabola that has an x-intercept of 1 and minus 1. And it's shifted down, so its y-intercept there is minus 1. If I want the absolute value of that, well, all these sections that were positive, they're still going to be positive. So the equations of these sections is still x squared minus 1 and x squared minus 1. However, this section between minus 1 and 1, x squared minus 1 is negative. So I need to multiply that by minus 1, or on a graph I would reflect that to sketch the absolute value. So the equation of this branch is minus outside of x squared minus 1. Okay, so x squared, the absolute value of x squared minus 1 is really a piecewise function. It takes the rule x squared minus 1 as long as x is less than or equal to minus 1 and x is greater or equal to 1. But it's going to take the rule negative x squared minus 1 for values between 1 and minus 1. Okay, and so when we approach from the left, which we will be doing, we will be approaching this way, we need to take care with which equation we are going to go with. So back to our limit here. We have the limit as x approaches 1 minus, and x minus 1 is on the numerator. But when we're approaching 1 from the left, the absolute value of x squared minus 1 is this equation minus outside of x squared minus 1 here. So we can simplify. We can simplify because x squared minus 1 factorizes to x minus 1 times x plus 1. We can see x minus 1 is a common factor on top and bottom. So this is the limit as x approaches 1 from the left of minus outside of x plus 1. Now we can see this is a continuous function at x equals 1, and so we're able to substitute. So I'm actually going to substitute now and get 1 divided by minus outside of 1 plus 1, or minus a half. Okay, notice we're still approaching 1. We're not approaching -1. I'm approaching 1, so I'm putting x equals 1 in. It's just that I'm coming from the left, and coming from the left means that we're taking this branch and this equation minus outside of x squared minus 1. So this is our one-sided limit of this expression. Question 3 is asking us to calculate a derivative from first principles. So we're given f of x is x squared minus 5. If we learn some rules for differentiation, we know that x squared minus 5 will differentiate to 2x, but we're being asked to differentiate from first principles and use this limit of f dash of x as the limit as h approaches 0 of f of x plus h minus f of x divided by h. I've drawn a diagram over here just to remind you where this definition comes from. So remember, if we have a function that I've drawn, so in particular I've drawn x squared minus 5 here, and at a particular value x, and then h units along at x plus h here, we're going to join a chord, right? And we're going to find essentially the average rate of change from x to x plus h here. So the difference in the function value is f of x plus h minus f of x, and the difference in these x values is h. So the gradient of this chord, or the average rate of change from x to x plus h, is f of x plus h minus f of x divided by h, this expression here. And when we take the limit as h approaches 0, we're finding what the instantaneous rate of change is, or we're finding what the slope of the tangent at x is. When h gets smaller and smaller and smaller, the slope of this chord becomes the slope of the tangent at x. So this is just to remind you where this formula comes from. So let's calculate. F dash of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So in this case, our function is x squared minus 5. So whatever the input is, we square it and we subtract 5. So if x plus h is the input, we will square that and we will subtract 5. So this is f of x plus h there. Minus f of x, well, whatever the input is, x, we will square it and we will subtract 5. So that's f of x there. And this is all divided by h. Now we want to simplify until we can evaluate this limit. At the moment, if I put h equals 0 in, I get x squared minus 5 minus x squared minus 5. That gives me 0 divided by 0, which I can't evaluate. So I'm going to simplify until I can. Okay, so x plus h all squared is x squared plus 2xh plus h squared minus 5, and now we're going to minus x squared and plus 5, all divided by h. We can see x squared minus x squared is 0, and minus 5 plus 5 is 0. So we end up with the limit as h approaches 0 of 2xh plus h squared divided by h. Now, I still can't substitute h equals 0 in, because I will still get 0 divided by 0. However, notice that h is a factor of the numerator there, and I can simplify this by cancelling those factors of h. So this is the limit as h approaches 0 of 2x plus h. So when h approaches 0, this is going to approach 2x. 2x plus 0, which equals 2x. So from first principles, we've worked out that x squared minus 5 does indeed differentiate to 2x, which is what we would expect it to do. Question 4 is asking us to find the absolute maximum and minimum values of a particular function over a closed interval. 0 less than or equal to x is less than or equal to 3. That's your closed interval from 0 to 3. So we could sketch this and we would be able to determine where the maximum and minimum values occurred on a sketch. We'll probably draw a sketch afterwards to indicate what's going on. But the idea of this question is that we can actually work out the absolute maximum and minimum values just by seeing what's happening at the critical points. So the absolute maximum minimum values on this interval, this closed interval from 0 to 3, will occur at a critical point. So what are the types of critical points you can have? Critical points can be stationary points. So maximum and minimum values can occur when f dash of x is 0. They could occur at the end points. So the highest or lowest values could occur at 0 or 3, or they could occur at points where f dash of x doesn't exist. So let's call them non-differentiable points. Okay, so they're the only places where you will find the absolute maximum and absolute minimum value. So instead of sketching it, we just can examine what these critical points are and find the absolute maximum and minimum values of those. Now, there are no non-differentiable points. We have a polynomial here, x to the 4 minus 8x squared, and that's differentiable everywhere. So there's none of those. The endpoints, well, they're easy to evaluate. We have f of 0 and we have f of 3. So f of 0 is 0 to the 4 minus 8 times 0. That's just 0. And f of 3 is 3 to the 4 minus 8 times 3 squared. So what's that? That's 9 nines minus 8 nines, which is one lot of 9, which is 9. Okay, so the maximum and minimum values could be the 0 and the 9, or the other way around, but they could also occur at the stationary points. So we have to examine the stationary points, but on this interval from 0 to 3. So stationary points will occur when f dash of x is 0. F of x is x to the 4 minus 8x squared, so f dash of x is 4x cubed minus 16x, and we want to solve that equals 0. So I can factorize this. I can at least take out a 4x and be left with x squared minus 4, but I can further factorize that into x minus 2, x plus 2 there. So stationary points will occur at 0 and 2 and minus 2, except that x equals 0 and x equals 2 are the only ones in this domain from 0 to 3. So note, x equals minus 2 is not in this interval from 0 to 3. Okay, well, we've already evaluated f of 0. That was an endpoint anyway, that's 0. But f of 2 could be a maximum or a minimum. So let's see what's happening at f of 2. Well, f of 2 is 2 to the 4 minus 8 times 2 squared. So that's 16 minus 32, which is minus 16. Okay, so the absolute maximum and minimum values have to be one of these values. The 0, minus 16, well, that's the same 0, or 9. So there are no non-differentiable points there. So we can see that the lowest value, the minimum value, is minus 16, and the highest value, this maximum value, must be the 9 here. So hence, the absolute maximum So the absolute maximum value, or the absolute maximum, is 9. That occurs when x equals 3, but the actual value is 9. And the absolute minimum value is minus 16. That occurs at 2, but the actual minimum value is minus 16. Let's just put that onto a sketch to see where all these fit together and what's really happening. So we will just quickly sketch y equals f of x here. So x to the 4 minus 8x squared, I can factorize that. X squared comes out. X squared minus 8 is left behind, and then we can further factorize that into x minus 2 square root 2 and x plus 2 square root 2. So there's a double root at 0 and single roots at square root of 2 root 2 and minus 2 root 2. So this graph actually looks something like this. Should be symmetrical. That's not quite symmetrical, but it will do. So this is 2 square root 2 here. This is 0 here. And this is minus 2 square root 2. Now, we were after the maximum and minimum values in the interval from 0 to 3. So maybe I'll just get this black text to here. So we were only interested from 0 to 3. So our calculations here should all make sense. F of 0 is 0. That was a stationary point and it was an endpoint, so that makes sense. F of 2 was minus 16. So that was a local minimum here. So that was the lowest value of the function in that interval, so that makes sense. And f of 3 was an endpoint, and f of 3 ended up being 9, and we can see that's the highest value of our function in this interval. Okay, so just graphing it, you're able to put things all together and see what's going on with the stationary points, the end points, and you can see there are no non-differentiable points as well. In the final question on this test, you are asked to find the gradient of the tangent to the curve given by y equals x squared outside of x minus 1 at the point 1, 0. So all we need to realize here is that the derivative is the rule that tells us the gradient of a tangent to the curve. So y equals x squared, x minus 1 is our curve. It will be easier to differentiate this if we expand it rather than use a product rule. Now y dash or dy dx is 3x squared minus 2x, and this is the rule that will tell us the gradient of the tangent or the slope of the tangent at any given point. So when x equals 1, right, at the point 1, 0, x is 1, y happens to be 0, but x is 1, dy dx is 3 times 1 squared minus 2 times 1, which is 3 minus 2, which is 1. So this is the slope of the tangent to the curve, or the gradient, at the point 1, 0. So hence, the gradient of the tangent at 1, 0 is 1. So on a picture, what does that look like? Well, I know how to sketch x squared, x minus 1. It has a double root at 0 and it has a single root at 1. So I know it's coming down here and having a double root there. What this is saying is that if you zoom in and zoom in and zoom in to this point 1, 0, then this curve will start looking like a straight line, and that straight line has a gradient of 1, that gradient of the tangent. So that has a gradient 1 there. So that's the end of this test.